want to change my domain a little bit. So if my u goes from 0 to pi, v goes from 0 to h, what will happen?
The front half of that?
So if u goes from 0 to pi, that means you cannot rotate for a whole circle anymore, right? You need to cut the negative parts of x-axis, right?
Yeah, yeah.
So basically, if
The left half is going to go away.
theta goes, if u goes from 0 to pi, I basically go from here to here, right? You with me? This means I need to cut through this xz plane and remove the left part. Okay? So in the end, we're getting a half cylinder. So this is the upper half, this is the right hand side. Okay? So if I make different restrictions of the parameter, you're getting different pieces on the same cylinder. Everything? Okay? Not only in this part, I can modify the restriction of u and v in order to get different pieces of the cylinder. There's also an inherent orientation here. But we will talk about that in a minute. Right now, I want to introduce a couple of more surfaces so we can get familiarized with their representation in a parametric form. So now I have v cosine u, v sine u, and v. Okay, so this is a parametric representation of what? Alright. And also, I want you to compare this equation with that equation. Only the parametric form. In that equation, z has no relation with x, y at all. So immediately you should know that it's a cylinder. But for this parametric form, the z component is also included in x, y. So this is definitely not a cylinder anymore. Okay? This is definitely not a cylinder.
Be a cone?
It is a cone if you're very familiar with the cone equation in x, y, z representation. One thing we can do is to eliminate u and v. Okay? I don't want you to do guessing all the time. I want to give you a very universal way to get the x, y, z equation. So here I want to eliminate u and v. One thing we can do, and here is the difficult part comparing to the line integral and parametric equations for the curve. The parametric equation of a curve, you only need to eliminate one variable. All right? Now we have to eliminate two. Okay? So this is my x, this is my y, this is my z. When I see cosine and sine, instinct tells me I want to do square. So I want to do x squared plus y squared is equal to the coefficient square, which is just a v squared. But that one is just a z squared. So you have to use three components in order to get the equation. So in the x, y, z equation, is x squared plus y squared is equal to z squared. So it did define a cone. This one defines a cone in the z direction. Okay, in the z direction. Again, I'm going to play around with the same thing as to restrict my parameters and get different pieces of the cone. So if this is the equation of a cone, you actually get an infinite cone up and an infinite cone down. All right? You actually get a cone opening to up and opening to down, with both axes as the z-axis. Okay? So this is the equation. And again, if you look at what the roles u and v play, okay? If you look at what the roles u and v play, u still plays the role as the rotation along the axis, all right? So this is the angle you rotate along the axis. V is still talking about something related to z, right? V is still something related to z. However, on one hand, z is talking about a height in the z direction, all right? So v defines a z component, which means if I have a v value, I know how high it is. But simultaneously, I also know the following. V is the radius of the opening. Can you see that? Mm-hmm. So if I have a height v here, this radius is also equal to v. Are you with me? This radius is also equal to v, because v is defining x component and y component by cosine and sine. So v is also the radius if you cut through the cone and get an opening right here. Okay, and that's essentially why, if you still remember the triple integral and double integral we did before, this angle is 45. Right? Because this line and that line of the same length. Okay. Now I want to do the restriction u and v here. If I have the restriction u is between 0 and 2 pi, v is between 5 and 7. Okay. If v is between 5 and 7, which piece am I going to get? So definitely not the lower half of the cone anymore, right? Because v is talking about the height. So we need to cut it from height equals 5 to 7. And then we need to cut the lower than 5 part and upper than 7 part. So this is going to be a piece of a cone. Okay, u goes from 0 to 2 pi, so I'm going to get the whole round. Whereas v is the height, goes from 5 to 7, so this is a piece of a cone. Okay, and this parametric equation together with the range of u and v, the two parameters, is going to give you the piece of a cone on somewhere. Okay, so the parametric equation is very friendly to work with, mainly because you can stick your restriction of u and v and get whatever the piece of the surface you need. Okay, questions?
How did you find 5 and
Oh, 5 and 7 are just two random numbers, I think. Okay, you can have any number you want, and you're getting different pieces of the cone. Okay, for instance, if I allow v to go from 0 to 7, I'm going to get the vertex here. Right? Okay, so questions? Now I want you to give me the parametric equation rather than I give you. I have the x, y, z equation defined by x squared plus y squared plus z squared is equal to rho squared. So in the x, y, z equation, tell me immediately what does it define? What does this equation define? Sphere with radius rho center at the origin. All right? This is the sphere we have been studying, especially in the spherical coordinate system. Now I want you to give me the parametric equation for the sphere. Forget about the restriction for now, just the parametric equation. I give you the hint, we already did that. I need to assign, first of all, I need to assign two parameters, right? So I need to assign two parameters. The parameter as the letter doesn't really matter. You can use u, v, w, x. You can use whatever letter you want. What if I say, let's use two parameters, phi and theta. And then, how do I define x, y, z?
rho cosine?
Rho
I mean 5 here.
sine phi
Oh,
cosine theta. Remember, we did the link x, y, z to the rho and phi equation, right? Rho, phi, and theta equation. So when we introduced the spherical coordinate system, we actually already touched on the parametric equation of the sphere. Okay? So y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. Okay, very good. So if I have two parameters, rho and theta, then these equations coming from the spherical coordinate system is already a parametric definition of the sphere. So this is equal to x, this is equal to y, this is equal to z. So you can easily take, going from phi and theta, you square x squared plus y squared and plus z squared, you're going to cancel all phi and thetas. Right? So if you square these two, you're going to cancel theta. And then adding together with the square of the z component, you're going to get exactly rho squared. So this is a very nice parametric equation of a sphere. However, if in your online homework and the software is very stubborn in choosing the u and the v as the parameters, if you don't like it, but in order to grab some points in the online system, this is still rho sine u cosine v. I'm just choosing the letters. Okay, rho sine u cosine v and rho cosine v. Okay, If the system insists you to use U and V, you just need to change from phi and theta to U and V. But basically, they're the same thing, just different letters. Okay? Question? Now, I still want to do the same. I want to look at the sphere and see what piece will I get if I restrict the parameters. Okay? So now let's stick with U and V. If I have U bounded by 0 and pi over 4, V bounded between 0 and 2 pi, I want to see which piece of the sphere will we get. Again, because now we're using UV as the parameter. U in this case is talking about the angle formed between the ray and the positive direction of the z-axis. That was me? U is talking about the angle between the ray and the positive direction of the axis. And V is talking about the rotation along the z-axis. Okay? V is the angle you can rotate along the axis. So U goes from 0 to pi over 4, which is essentially go from a positive direction of z-axis and an angle formed by a ray and a positive direction of axis given by 45 degrees. All right? And everything above this ray will be included. And the V goes from 0 to 2 pi, so I still will be able to go a whole round. So everything above this ray for a whole round will be included. So basically, with these two restrictions, you're getting a cap. That was me? You're getting this cap. Okay? So I'm going to erase everything else. This is the cap you're getting. Okay? This is the 0 to pi over 4. Okay? I don't know that. I'm just drawing that roughly. It's not a. Oh, this number assigned.
Yeah,
this number assigned is a random number assigned. Okay?
But how do you know on the graph where to erase it from 0 to pi over 4? Because you just drew it out, but how do you know where to erase the?
Oh, the part I erased are all the angles which are going to go beyond pi over 4. Right? When pi U is equal to 0, I'm at this ray. Right? When U is equal to pi over 4, I'm at this ray.
Which rotates,
U is
right?
restricted between these two, so I have to make sure this ray is within this range. All right? So we're not getting the one that go beyond. Right? So the only thing which is left on the sphere is this small cap we have. Okay? Any questions? Okay? So let's say if I change my restriction a little bit, U goes from 0 to pi over 4, V goes from 0 to pi. What happens?
The right
You
side
need
of
to
the
transfer your cap into
2.
2 and throw away
The
the
left
1,
side.
which is in the negative direction of y-axis. So essentially, I needed to cut it through in the y-axis. And then I'm going to throw away the negative part. Okay? So this is what you will get. Okay, half of a cap. So by choosing the restrictions of the two parameters, you can restrict your parametric equation into any piece you want in the sphere, and in any piece you want on any surface, basically. So here are the very important examples. Cone, you definitely have to know how to parametrize it, how to find the parametric equation. Sphere, extremely important. And this one is a little bit easier. Cylinder. You definitely have to know how to get these three objects into the parametric form, and also how to find corresponding piece when you have the restrictions for parameters. Okay? Questions? So next, what I want to do eventually is to how to do integral on these surfaces. So now we have a surface. So now we have a surface but also we have its parametric form, which is defined by u, v as the parameter, okay? And I write this as the vector form of the parametric equations. So if you compare this equation with the parametric equation of a circle, of a curve, which is pretty similar here, right? Over there you have a vector with respect to one parameter. Here we have a vector with respect to two parameters. So in this case, my x is defined by a function of uv, y is defined by a function of uv, and z is defined by a function of uv. Okay? So this is the general form of surface. For instance, in this case, my x uv is equal to rho sine u cosine v. My y uv is equal to rho sine u cosine v, and my z uv is equal to rho cosine v. Right? So the general form, x component, y component, z component, they are all defined by some function with respect to two parameters here. Okay? And also u and v as a pair of variables is coming from restriction or a range. Okay? So for instance, in here, the restriction is u is bounded between 0 and pi 4, and v is bounded between 0 and pi. Right? So in the general form, you have a vector defining the parametric equations, and also a restriction about the two parameters. Okay? This one will give you a surface. More strictly speaking, some piece on the surface. Okay? Do you agree on that?
Mm-hmm.
And then I want to define the surface integral of a scalar function on x. So we'll always begin from the surface integral of a scalar function, and then we'll move to the surface integral of a vector field. Right? Exactly as what we did for line integral. Line integral of a scalar function, and then the line integral of vector fields. So the line surface integral of a scalar function, which is given by f x, y, z here, will be defined in the following. So the surface integral of a scalar function on a surface. This is the terminology, this is the notation here. I'm using a double integral here, essentially because the surface is a two-dimensional object. So this has to use a double integral. Line integral, essentially the curve is a one-dimensional object.